Okay. Hello. Is my audio all okay? It is. Okay, nice. Oh, I assume the rip was for the fact that I had to restart the stream. Yeah. Um, I have to do that basically every time. It's quite annoying, but there's something goes strange with the audio when I don't do it, so I have to do it at the start. But then after that, it's usually fine. Uh, yeah, it is quite weird. But yeah, anyway. Hello everybody. Oh, Sly subscribed with Prime. Thank you very much, Sly. That's very kind of you. Um, yeah. So there are two interesting questions I've got today. The first one is the one you can probably see is slightly drawn on the screen. That was posted in my Discord, which is this sort of interesting mechanics problem where initially you imagine this thing is kind of left at rest. So this second mass M2 here is just dangling horizontally, some height above the ground. And then if I understood the problem the way the person asked it anyway, but even if I didn't, this problem in itself is quite interesting. If you leave this this mass M2 dangling and then let it go, of course, there's a smooth pulley here, so it'll start to get accelerated downwards. And when it gets accelerated downwards, it'll, pull on this second mass on top here, which is not attached at the bottom, and it's all smooth at the bottom, so it can just slide over. So this will start accelerating to the right. And this in turn will actually cause the larger mass, which is on wheels, to start moving to the left. So this whole thing, just by releasing the second mass M2 from the pulley, this whole thing will start moving to the left. So it's quite an interesting mechanics problem. But of course, what happens is as this thing on the wheels here starts moving to the left, then it'll mean that this thing starts swinging out to the right at some angle. Oh yeah, that's the problem. Oh, A1 is relative to the surface of the trolley. Okay, that's fine. So I haven't. So the way I'll look at it is not to explicitly find A1, because I think actually, as far as I'm aware, this problem I don't think you can solve it exactly. I think you can only solve it using a number of approximations. I think if you found all the equations of motion for this, I don't think you could solve them exactly without doing some approximations. As far as I know, in the same way, you can kind of imagine that you might not be able to solve it exactly. In the same way that if you write down the equation, for an ordinary pendulum, if you've got an ordinary pendulum that is suspended or released from some angle theta, if the pendulum has got mass m, and the pendulum has length L, you probably know the equation that this thing will oscillate with time period. What is it? It's is it L over G or G over L? Well, it's got to be L over G by dimensional analysis. So you know that this thing will have simple harmonic motion in this way, L over G, where G is the gravity. But this is actually only valid when theta is a small angle. So you have to apply the small angle approximation to this system. Yeah, exactly, for small angles. But exactly solving this thing is quite a bit more difficult, and I think you have to do it numerically. You'll have to integrate numerically the stuff you get and solve the differential equation in that way. So it's only really exactly solvable when you make this simplifying approximation. And if you notice here, we've got another thing that is sort of, like half of a pendulum with some angle theta. So for large angles theta, it's reasonable to assume that this thing will become a little bit tricky and might not be exactly solvable. And I think it turns out that is the case. The equation I get anyway is totally unreasonable. So what I've done here is I've written down, or I've defined all my variables. So x is what I call the distance the pulley has travelled to the left. Theta is this angle from the vertical that the rope has swung that is connected to M2. And then we've got some initial conditions. So at t equals 0, we're assuming that this rope here is just, straight down. It's not swung out at all. So R here is the length that the mass M2 has kind of pulled out of the pulley, has pulled this along. So at some point, you know, if the thing starts off at rest here, this length here will be what I've called R0, this initial length of rope that is between the pulley and the mass. X is 0, at t is 0, the thing, you know, I measure x is 0 from this point here, or, well, some point before, because then this won't have swung out by then. I also say that theta dot is 0, r dot is 0, and x dot is 0. Okay. You always get the impression from popular science books that physics is so elegant and perfect, but it's all approximations. It is all approximations. I mean, a lot of things are elegant and perfect. I mean, pretty much everything is a simple harmonic oscillator, and if you see the world in that way, then everything is very nice and exactly solvable. But yeah, a lot of physics is quite dirty, and you have got to do quite a lot of approximations. But that's part of the fun of it, I think. So these are all of our initial conditions I've written down. Now, as a pre-warning, the equations I get, I don't even go far enough with that I need to use these initial conditions, because the equations you get are quite horrible, and I can't see any way of making them particularly nicer. So the way that I've approached this is to use the Lagrangian formalism. Instead of thinking about forces and dynamics and stuff like that, which I think would be even more difficult. The method, you know, of using Lagrangians and the Euler-Lagrange equations is really a very sort of cheap and easy way to get the equation of motion for your system. If you were to actually try and find the equation of motion for this using Newton's laws, I think it will be quite difficult. The main difficulty is in that this thing here, you know, this large mass is accelerating to the left with some acceleration a. So, although technically you could say, well, let's think about motion in the rest frame of this object here. The issue is that this rest frame is not inertial because it's accelerating. So you kind of have to know what the acceleration is or go back and solve it at the end to find what this reference frame would even mean, which is a little bit tricky. So I think using the Lagrangian formalism is quite a lot easier. So here is just an extra drawing I've done of the corner with the pulley with the masses on. So here I've left the masses as dots just because it's a little easier to draw lines coming off of them. So the crucial thing here is to note that, you know, this second mass that is attached to the string, it has two components to its motion. It's got tangential motion, you know, as it's sort of swinging out, motion due to this angle changing, and it's got radial motion due to the string, you know, being pulled over the pulley, it drawing more rope away from this side and onto this side. And from this, you can realize that R dot here is the rate at which you're pulling rope over the pulley, and therefore it's also got to be the rate at which this second particle m2 is moving to the right with respect to this larger mass, with respect to the pulley. Okay, so from the perspective of the large mass, capital M, or the pulley, the mass on top is moving to the right with speed r dot, which is the same as this radial speed r dot as the second mass. Okay. But then remember, I defined x as this position that the pulley has moved to the left, this position like this. So this entire system now, this entire solid part of the system anyway, with the mass and the wheels and the pulley, is all moving to the left with speed x dot. Okay, so instantaneously this system has some speed x dot, which will change. X dot will increase because the whole thing will accelerate, but instantaneously it's all moving to the left with x dot. Okay, so these are the relevant parts of our motion, these things I've drawn in orange. And these angles here, you can justify to yourself, you know, by some trigonometry that if this angle here is theta, this angle here is also theta, and therefore this angle here is 90 minus theta. Okay. So the Lagrangian of a system like this, classically is just the kinetic energy that I call T minus the potential energy V. Now the potential energy is very simple, because everything is staying at the same horizontal level, except for the mass m2. You know, m1, it stays just above the box. The large box, capital M, is on wheels on the floor. It's not changing its vertical height. So the only important contribution to the potential energy is the potential energy m2. So if I take my, my baseline here, then the potential energy is just going to be minus this length here times by mg. Okay, so that's simple enough. That's what I've got here. The potential energy is minus mg times that height that I drew, this height here, which you can see is just going to be r, this length, times cosine theta, and that'll give us that length here. So that's straightforward enough. The kinetic energy is a little harder to get. So if we look first at the kinetic energy of m1, so m1 relative to the box and the pulley has got a velocity r dot, but then the entire pulley system and the box is moving to the left with speed x dot. So the net speed in the rest frame, the laboratory frame that is watching this system unfold, is going to be r dot minus x dot, is that net speed in the horizontal direction. So that is all squared for the kinetic energy of particle m1. Particle m2 is the most complicated one. So now you have to think about the horizontal and the vertical motion of particle m2. So it has a horizontal component going to the left that is due to this entire frame moving to the left by some speed x dot. And then it has these two components here, the tangential velocity and the radial velocity. So what we have to do is we have to resolve the velocity components orthogonal to each other. So you have to find the component of the tangential velocity horizontally, which is the shadow of this orange vector here. So that's going to be r theta dot, the length of this, multiplied by cosine theta. So that is where this appears, this first term in the horizontal speed. Then added onto that, because we're resolving positively to the right direction, okay? Added onto that, we also have the radial speed, which will contribute, it has a magnitude of r dot, and now the angle of its shadow in the horizontal direction is times cosine of 90 minus theta. And cosine of 90 minus theta is a trig identity. So cosine 90 minus theta is just equal to sine of theta. So that is why this part of the horizontal speed appears like that. And then lastly, we have the horizontal speed now to the left due to this entire thing moving in a leftwards direction. So we have to subtract x dot, the speed this thing is going with, to the left. So that is our horizontal velocity. So our net velocity of m2 in this direction, which we could call vh. And now what we have to do is we have to find its net vertical velocity, vv, and then its total speed is going to be the sum of the square of those speeds. Okay, so that is why I've got the horizontal speed squared, and I'm going to add it to whatever the vertical speed is squared, which will give me the total speed squared, because that's what appears in the kinetic energy, the total speed squared. So the vertical speed of the mass m2, well, it's got a positive component due to this vector, so that is going to be r theta dot times sine theta is the velocity upwards. It has now a negative component due to the r dot vector, so that is r dot times sine 90 minus theta, and sine 90 minus theta, that is the same as r dot times cosine theta. So that is why we get a cosine theta here, okay? And again, this is all squared because you're doing the horizontal speed squared plus the vertical speed squared. So that's where we get the kinetic energy of mass m2 from. And then simply enough, we just need the kinetic energy of the large mass, the box on wheels that this whole thing is on. So this whole box has got mass capital M, and this whole system is moving to the left with speed x dot. So its kinetic energy is half capital M x dot squared. Okay? So that's the kinetic energy and the potential energy. And then the Lagrangian is the difference between them. The difference between kinetic and potential. I think actually a couple of weeks ago we spoke about where this comes from, in classically at least, why it is that the Lagrangian is this t minus v, which is minimized somewhere, I think. I can't remember which date it was, but we spoke about that at some point. So if you combine all this together, t minus v, you get this rather ugly looking Lagrangian. Yeah, exactly. Hamilton's principle, exactly. And from this ugly Lagrangian, the way you extract your equations of motion from it is to use the Euler-Lagrange equations. So that is that the partial derivative of L with respect to any one of the coordinates is equal to the time derivative of the partial derivative of L with respect to the time derivative of any one of the coordinates. So we'll get three equations of motion, one for choosing Q is X, and likewise then Q dot would be X dot if we choose Q is X. Another one for Q is R, and another one for Q is theta. Okay? And now if you do that, that's a horrible amount of algebra, and you get some horribly complicated equations, which, when you look at them, I think, unless they're very, very deceptive looking, I don't think there's any way you can solve them exactly. I'm very confident, well, I'm pretty confident that this system is not exactly solvable. But if anyone manages to, if anyone has any ideas and wants to go through all the algebra and find the Euler-Lagrange equations for this entire Lagrangian, be my guest and let me know. But I didn't want to do that, so I didn't. So what I did instead is I decided that I would do this to first order in theta and first order in theta dot. So when I say first order in theta and first order in theta dot, so of course you should be able to tell from this that I'm going to neglect terms like theta squared and higher, theta cubed, theta to the fourth, etc. This is under the assumption that the angle is small. Just like the small angle approximation I mentioned when we talked about an ordinary pendulum. But now I'm also making the assumption that the angular speed is small, and that is that this particle, it doesn't, very quickly whiz off at some high speed. And not only that, I'm assuming that both of these things are small, and they're small in a similar way, such that the combination theta times theta dot is also small. So these are assumptions that are, somewhat weighty, but I think they're quite reasonable. So my justification of it, yeah, exactly. You always got to use small angle. My justification of it is that if the mass of the box is much larger than the mass of either one of the two weights, m1 and m2, so I'm saying if this mass here is much larger, then the effect of this second mass m2 falling down, it's not going to exert a large reaction force on the pulley. So therefore the pulley is not going to exert a large reaction force back on the mass, because, or rather proportionately, it's not going to exert a large reaction force because, the weight of these things here, which will be related to the size of the reaction force that is produced, will be much smaller than the mass of this large object. So the system is not going to move very quickly. It's not going to shoot away. So I think it's reasonable to say that in this regime where the mass of the trolley is much bigger than the mass of these two other masses, particularly the mass, well, actually no, it's equally important that it's the mass capital M is much bigger than M1 and M2. In this regime, then I think it's reasonable to say that theta should be small, theta dot should be small, and also theta dot, and therefore we can ignore terms like theta squared, theta dot squared, theta times theta dot, and so on. Okay. And the reason I chose this, I kind of preempted this, that the reason this is convenient is because now what I can do is I can apply the small angle approximation to the terms in my Lagrangian before doing any differentiation. Okay, so say I wanted to keep terms like theta dot. Say I didn't decide that this term here was small. Then I would actually have to do some differentiation before putting the small angle approximation in. Okay, because say for example you have a cosine theta. If you apply a small angle approximation, say that cosine theta is roughly 1, to leading order, then when you differentiate cosine theta, you get nothing. When you differentiate 1, you get nothing. But say I instead differentiated cosine theta and then said I only wanted things to leading order. Well, if you differentiate cosine theta with respect to time, you get minus theta dot times by sine theta. But if I take that to now, if I expand first order in sine theta, expand sine theta to first order, I get minus theta dot times theta. So that is a term here that if I was including terms like this, of theta times theta dot, I wouldn't be allowed to just get rid of the cosine thetas before differentiating, because I would miss something. But I'm kind of preempting that I don't want to keep cosine thetas in here right from the beginning, because it's going to be annoying. So I'm saying, well, let's also say that theta times theta dot is small. Which I think is fairly justified. So I don't think there's too much of a problem here. I mean, and even with these assumptions that I'm ignoring all terms like theta, theta dot, theta times theta dot, the equations are still not very nice. And I think actually still you might have to use a computer to solve them. But I haven't tried it too much once you get the final equations, but I'll show you what the final equations are you get anyway, and the kind of process for doing this. So what I've done here to get this approximate Lagrangian that is valid below terms of this order, so is only valid for first order, or will, when I get the equations of motion, will only be valid to first order in theta and first order in theta dot, is I've essentially just said cosine theta is approximately 1 in this thing from the small angle approximation, and sine theta is approximately theta. Ooh, theta, not 0. So anywhere you see a sine theta, I put in a theta. Anywhere you see a cosine theta, I put in a 1. Okay. Now I could have written it as 1 minus a half theta squared for cosine theta, and then differentiated, but I think actually all these terms, I would still then end up with terms like theta times theta dot every time, which I've said I'm going to neglect. Okay. So this is my approximate Lagrangian. Now I have to apply the Euler-Lagrange equations. And like I said before, there are 3 of them. There's one for the x-coordinate, one for the r-coordinate, one for the theta-coordinate. So the first one is for the x-coordinate. So on the left-hand side here, I've got the derivative of the Lagrangian with respect to x. So x, not x dot. Remember, because these are partial derivatives, you treat the x and the x dot independently, actually, when you're doing this differentiation. Okay. So if you look here, there's no term in the Lagrangian that depends explicitly on x. There's a term that depends explicitly on x dot, but these things we treat as independent in the analysis. Okay. So that means the left-hand side of this equation, which in this case is dl by dx, will just be equal to 0. So then I have to look for the right-hand side, which is this time derivative of dl by dx dot. Okay, just substituting q is equal to x here. And now there are some terms that depend on x dot, certainly. There's a term here, a term here, and a term here. So this first one gives me this term here, differentiating with respect to 2x dot. The second one here, this gives me these terms, and the third one gives me this last term, m times x dot. And then I have to take the time derivative of these and set them to 0. Or equivalently, what I could have done is I could have just said, because the time derivative of this is equal to 0, maybe this is a nicer way to write it, that just means that the thing inside of the time derivative, let me maybe put it here, is equal to some constant. Maybe call it d. So where that is some constant in time. Now let me just make a little bit more room here, actually. And again, of course, I'll post all of these on my website afterwards, so if anyone wants to check my algebra, do feel free, because it is far from unknown for me to make algebra mistakes. So let me just extend the box. These are sort of equivalent. All this, okay? So we could also write the equations we get from this first one in this way. Was the chain rule used in differentiating with respect to x dot? Yes. So here, for example, I use the chain rule, so I bring down the 2 here, which gets rid of this 2 here, and that's differentiating, the outer function, if you like, and then I've got to differentiate the inner function with respect to x dot, which is this r dot minus x dot. So that's why I pull out this factor of -1 here. Oh, I see what you mean. Oh, bugger. Yeah, that should be, in that case, that should be an... yes. I'm not sure if that's what you were pointing out, but you have just made me realise a mistake. That should be r dot minus x dot there, in fact. Checking that chain rule. Yeah, oh no, yeah, thank you very much, exactly. Have I made a similar mistake anywhere else? So I bring down a 2 here, that gets rid of that 2. Then I differentiate this inside bit with respect to x dot, except now that derivative with respect to x dot now just brings a -1, and then I've got the inner part as before. Same thing here. So that's all fine now. I just have to now correct this extra line here to yeah, no, that's fine. So that equation is correct, but then I should also have a well, somewhere in here there should be a minus m1 r dot. Yeah. Where can I cram that? Well, I'll just put it, for the sake of correctness, I'll put it there. Minus m1 r double dot. Okay. So yeah, you're right. So that has modified this equation slightly. Okay, great. Thank you. So that's the theta, sorry, that's the x equation. This one here I think is probably the nicest way to write it, where this will be some constant that won't vary with time. The reason I know it doesn't vary with time is that this entire thing inside of here, differentiated with respect to time, is 0. Therefore, it can only be a constant with respect to time, the thing that is in here. And I just call this constant capital D. Okay. So that's all I've done. I've taken the inside of this bracket for the derivative and set the whole thing inside the bracket equal to some constant D. Okay. Then there is the R equation. So again, this one gets a little uglier. So the left-hand side here is what you get from differentiating with respect to R, the Lagrangian. So now I'm differentiating this thing with respect to R. So I pull out a term from here, as there's an R here. This will give me, again from the chain rule, it will give me m2 times by theta dot times by the entire bracket. Like that. Let's check that's what I wrote. That is indeed what I wrote. Okay. Then the second one with an R, the only other one with an R, is this term here, which simply enough, when you differentiate, just gives you m2g. Okay. And that is where this comes from. So this is all fine, this left-hand term. But now remember, because we're only working to first order in theta dot, that means I can immediately scrap these terms here. Well, rather, scrap these ones highlighted in red, because when they're multiplied through by this theta dot, they will become second order. So in the next line, I will have scrapped these. Then the right-hand side here is this time derivative of dl by dr dot. So now I need to differentiate the Lagrangian with respect to r dot. So I get a term here. Maybe I've made the same mistake here as I did before. So this should give me m1 times by r dot minus x dot. Did I do that? I did do that. Okay, I didn't make the same mistake. Nice. Then the other term with r dot is here. This should give me m2 theta times the entire bracket here. So let's check I got that. m2 theta times the bracket. That is correct. m2 theta times the bracket. And then the last one is this simple term here, which just gives me mr dot. m2r dot. Where am I? m2r dot here. So that's all fine. Then I just have to differentiate all these terms with respect to time, which is, a little tedious. So you get from this term, I just add a dot to everything in here. From this term, well, actually what I do first is I can realize that because of the theta out here, this term will be second order, this term will be second order. So these go away. So all I end up with is a minus m2 theta x dot from here, which I then differentiate, and it gives me a minus m2 theta dot x dot and a minus theta x double dot. But then I notice that actually this m2 theta dot x dot cancels an m2 theta dot x dot here. So this is all that is left, these terms here, and then I collect them in this way. Okay. Right, so that's the R equation. Then the theta equation, again, it's more of the same. I don't think I made any mistakes in this, but actually this one is the most... actually, this one was okay now I think about it. So you have to differentiate the left-hand side with respect to theta of the Lagrangian. So the terms that have a theta in, there's only one, which is this term here. So differentiating this with respect to theta will again bring down a 2 from the chain rule, and then I will have an r dot times by the bracket, like that. So that's what I should have on the left-hand side and nothing else, which I do indeed. And on the right-hand side, I've got the time derivative of this bit. And this bit here comes from differentiating the Lagrangian with respect to theta dot. And theta dot only appears here. So this just brings out a term m2 times r times the bracket. Like that. So that is what I should have inside the time derivative, what I've got there. Which I do indeed there. Okay, and then if I do this time derivative here, now using the product rule, I first differentiate the outer part. So I pick up an r dot here times this bit undifferentiated, and then I do the opposite where I now leave the outer bit here and differentiate this part here. But what you notice before I do this differentiation here, if I just add a dot here, as I do in the first step of the product rule, this whole thing here actually cancels the entire left-hand side. So these things both cancel each other, which is quite nice. So actually all I have is a 0 on the left-hand side equals this whole thing here I get from just having mr times, the derivative of this bracket here, which, when you work out will be r dot theta dot plus blah, 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 and it's all quite long. But actually what I can do instead is I can just say that I have... So this whole thing here is equal to 0. And this bracket, what is inside this bracket here, this longer part of the bracket, this is just the time derivative of this thing. So that is the time derivative of r theta dot plus r dot theta minus x dot. Okay. And this whole thing, again, remember, is equal to 0 because of this cancellation. Which means, again, just in the same way I did before, saying the time derivative of this thing is 0, I can then say the thing inside of the time derivative is a constant, which I call k. So I call this entire derivative k, and then in fact something even nicer I can do is I can say that this whole left-hand side here is actually also a time derivative of this function. If you differentiate this function with respect to time, you can see that you'll get from the product rule, differentiating this part, you'll get an r times theta dot plus an r dot times theta. And then from the second part, you still just get theta dot. So you can see that these two left-hand sides are the same as each other. So now I just integrate this whole thing with respect to time again. And now I extract a quite nice relationship, which is that r theta minus x is equal to kt plus c, where k and c are both just some numerical constants that you could find from the initial conditions. We've got enough initial conditions that we can find all of them. We wrote down about 6 or something. So this now would give you a way... exactly, yeah, the right-hand side is like a y equals mx plus c, exactly. So you've now got a way that you could get rid of all of the x's and have an equation just in terms of r's and thetas. And then I think you would have to solve r and theta numerically. Maybe you wouldn't, maybe you could do it exactly. But to know whether you could do it exactly would involve, rearranging this equation for x, going back to this equation, finding x double dot from the previous equation for x, putting it in, having one equation involving r and theta, and their first and second derivatives here, then doing the same thing and putting your expression now for x dot, which you get from the first expression, the one that was like r theta minus x is equal to kt plus c. You would put your x into there in terms of r and theta, and you'd get another equation for oh no, never mind, for r and theta. So you'd have two coupled differential equations for r and theta, second order differential equations, which I don't think would be very amenable to any nice analytic technique to solve. I think they'd be quite difficult. So you could solve them numerically, probably using some sort of Euler scheme, where you discretize your time intervals, and you can write your derivative of theta as being, the value of theta at some time grid point minus the value of theta at some earlier time grid point, or the one directly to the left, divided by your time step delta t. Kind of like the trick we did when we were looking at white dwarf stars, and we discretized this equation, if anyone watched that. Then I think you could probably solve it, but I think you'd have to get a computer to do it. I don't think you can just solve it exactly, which is a bit disappointing, as a theorist, that I don't think you can solve this exactly on its own. But I think it makes sense that it's quite a complicated problem. I mean, I'm perfectly happy to be proved wrong. If someone can find a totally analytic solution to this, maybe doing it in a different way, maybe I've done this in a slightly computationally heavy but not particularly intuitive way. If someone can think of a nicer way of writing it where it could be solved exactly, that would be very interesting. But as far as I can tell, it makes sense to me that this problem is not one you can solve totally analytically, and would be a little bit of a pain in the butt to do. And it certainly seems like it would be a pain in the butt. I mean, it was a bit of a pain in the butt to do, even with some simplifications. But yeah, so that's my rather unsatisfying answer to the question. Maybe if because it was Theoretical Phys that raised this in the Discord. Maybe if you fancy stretching your if you approximate all the masses as 0, well, yeah, that would probably fix it. I mean, yeah, even if you just set m2 equal to 0, you've just got a box set on another box. That's easy enough. Or if you set m1 to 0, you've just got a box on a flaccid piece of string that just falls and the cart stays still, which is not quite as interesting. Oh yeah, please do look at it once you start. I mean, the exciting thing is, Sly, you'll be able to look at interesting problems like this within your first year, I think. Definitely your first year, you'll be able to think about problems like this. And it's amazing how many problems you get using, fairly basic physics, which are not exactly solvable. Even the very simple case I wrote down earlier of just a normal pendulum, where you don't take the angle as being small, is not exactly solvable analytically. You have to, do some approximations and to get a nice solution that it's a constant simple harmonic motion. If not, it can be quite tricky. But yeah, so yeah, no, I mean, if anyone wants to stretch their coding muscles, then they could definitely have a go at solving this system of equations numerically. Doing a similar method we did when we looked at white dwarfs and discretize it using like an Euler scheme or something, and then write a piece of code that would time evolve it in these time steps. Get a sort of iterative equation from the differential equation, and then solve it in that way. Would be quite interesting, and you could produce some plots. I can't think of any reward or incentive I could give for someone that would produce the plots, but it would be very interesting. Could we do some more Lagrangian stuff in future office hours? Yeah, I like these problems. Maybe it would be nice at some point we could look at, because I think I quite enjoy doing some of this numeric stuff, like we did. I keep mentioning when we did the white dwarf thing. Maybe we could look at a double pendulum or something and try and write down, the equations of motion for a double pendulum, are simple enough to write down. In fact, they're very simple to write down. In Lagrangian form anyway. If you were to do it with forces and dynamics and torques and stuff, it's a little trickier. But if you do it in Lagrangian mechanics, a double pendulum is quite easy to get the equations of motion. The difficulty is the equations of motion are very difficult and they're actually chaotic. The solutions are very, very sensitive to initial conditions. So you can only solve it numerically. And in fact, your numerical solutions are extremely sensitive to initial conditions, such that if there's a tiny variance in your initial speed, your initial angle, your initial whatever it is for the double pendulum, you get totally different chaotic motion afterwards. So it might be interesting. Maybe we could live do the physics, then live code it, then live produce some pretty plots of this chaotic motion. Would be quite interesting. Maybe we can do that next week or something. If there are no other intervening questions, that could be cool. Could coupled pendulums with springs be done using Lagrangians as well? Yeah, oh yeah, so something like do it. Okay, Liam's vote is cast. That's final, we'll do it. So what, something like two pendula like this, or maybe one of them is like this, ignore this one, and they've got a spring between them and they're allowed to, to oscillate backwards and forwards, both of them. That's an interesting system, and that's certainly one you could write down, you could write down quite easily using Lagrangians. Oh, like normal modes, as in finding the normal modes of this system. Oh yeah, sure. That's also something you can do with Lagrangian mechanics. It's you get the equations of motion from, Lagrange's way of finding of doing this, just getting the equation of motion. And then for a normal mode, it's just an eigenvalue problem you have to solve, where there are these different allowed frequencies that this system can vibrate at. You can imagine there's the lowest frequency one where both of these pendula are just like this. Maybe there's one where they're like this, where they're bouncing the spring, and there might be some more complicated ones and of higher and different frequencies. But these will all be solutions you can find from the equations of motion. We'll learn Python and code some pretty animations. Yeah, my Python is pretty bad. I really can only do MATLAB, a bit of Mathematica, and a bit of Maple. Yeah, I should really learn. I wanted at the start of this year. My university offered like a course in C++ that I initially wanted to take because it's it's a bit more of like a big boy coding language that I think it would be good to know. But it was just too much. It would have been too much work to do, I think, alongside other courses and teaching and research stuff. So I never went along with it. But maybe next year, when hopefully maybe things will be a little calmer. Hopefully then I can do it, and that'll be interesting. But yeah, my coding is quite bad. But I think this is something we could code. The system of equations we've just got to, I think, is something probably you could quite easily program. Oh, you've got a brother taking computer science, so you think that'll help you a lot once you start your first coding courses. Yeah, I can imagine it will do. I mean, most of my friends are far more computer literate than I am. I've got some very bright, software-y, computer sciencey friends, which are go-tos when I have questions about this kind of thing. So it is very useful. It's good to make when you're at university. Well, I mean, actually, I'm referring to my friends before university, my school friends. But it's good when you're at university to make this, broad range of contacts, people that do different courses, not just physics, and also not just sciences. I think it's important to, to make friends with people that are doing courses totally separate to you. Things like music, and I have a lot of friends that are classicists that did classics and history and life sciences and all sorts. You can have so many interesting conversations with people at university that are just as interested in history or classics as you are in physics. So it's one of the great pleasures, I think, in meeting people with totally different interests to you, that think you're absolutely mad for liking physics, but then you think they're absolutely mad for liking their subject as much as they do and not physics. So it's a good pairing. So there was another question somebody asked. So somebody asked the question about I'm not exactly sure what the question was asking, but the question just said the Einstein field equation and then in brackets variant derivation. So I don't know if they're in the chat. Feel free not to identify yourself if you don't want to, but I'm not completely sure what that question meant. But I thought I could just talk about the Einstein field equations a bit and how I think the nicest derivation of them is. Now there are a few ways, so I'll mention the second way as well, which is to get them from an action principle. And action principles are really important in theoretical physics. All of particle physics, particle theory is written in terms of the Lagrangian formulation of quantum mechanics, in terms of these path integrals and stuff. So it's an important way of being able to do these things. But the way I think is most natural... Oh, hello, Rooster. Hi. The way I think is most natural, or most as historically accurate as well, actually, to think about the field equations is to think about them in terms of the equivalence principle. So the equivalence principle pretty much says that gravitational forces can't really be distinguished from accelerations. So you've got no way, say you were in an elevator somewhere in empty space and you were, you were very tiny, so you couldn't sense any sort of differences in the gravity at either side of the lift or something. You're a very tiny person in a lift in space or something. You couldn't really tell the difference between whether you were sat on a planet and felt the gravity of the lift pulling you down, or if you were accelerating upwards. Those two things would be equivalent to you. Okay, you couldn't tell the difference. Oh, Rooster says they have a new icon. Oh yeah, you do. I made you a VIP, I think. So I should make some other people VIPs too. I go on a bit of a spree and then I forget to add other people. So don't be offended if I haven't made you one. I'm sure I will get around to it. I just sort of forget. Okay, so that's what the equivalence principle says. Accelerations and gravitation are sort of indistinguishable. Locally, anyway, on small scales, you can't really tell the difference between them. Of course, gravity can look different to an acceleration, because as you know, if you think about the gravity of a planet from a point mass or something, this spreads out like 1 over r squared. The force does in Newtonian physics anyway. So there are slight differences. You're always being pulled towards the center. Exactly, tidal forces, like theoretical physics. You're always being pulled towards the center. You're never being pulled directly down. So if you have a large spatial extent, say you've got a point mass here, and you're some big long thing, your right end here would feel it being pulled in that way. Sorry, your left end would feel it pulled in that way, and your right end would feel it pulled in this way. So you'd be able to tell that you were in a gravitational field, and as opposed to if you were here and you were just accelerating upwards, you could tell the difference then. But if you're small enough, then it roughly just feels like it's going straight down, and if you're accelerating up, then it feels pretty much the same. So that's what they mean by local in this way. I think you might be the only person on the planet who thinks you're important. What a nice gesture. Whoa. That got deep, and I'm sure that's not true. But thank you. I do think you're important, of course. Yeah, anyway, so oh, and thank you for posting the emote, Machu. Yeah, I don't know why I did that. I should add some more emotes. I think they're quite fun, but I just added that one of me looking quite strange in a bobble hat. But yeah. So that's what the equivalence principle says. So what this also means, you can kind of take it the opposite way, or not the opposite way, you can take it another way and say that if you were to put yourself in one of these elevators in space, and you were to just leave yourself freely falling in a gravitational field, you would feel like you were just floating in empty space. Okay, so it's kind of then like, the gravity of you being pulled down is sort of cancelled by the acceleration in the same direction. Okay, so if you're freely falling in a gravitational field, you feel no gravity. That's this interesting thing, is that the reason we feel gravity, we don't actually really feel gravity on the Earth. What you feel is the Earth pulling up on your feet, pushing up on your feet. You don't feel the gravity of the Earth. You feel the Earth pushing up against you. If there was no floor beneath us, if suddenly the floor of the Earth just disappeared and there was nothing but the point mass at the center, you would feel nothing until you hit the point mass, obviously. But while you were falling freely, you would feel like you were in empty space. You wouldn't know you were about to hit into a very tiny, dense thing. You wouldn't know you were about to hit into a black hole or whatever. Thank you for posting even more of the emotes, Sly. Much appreciated. I need to remove them. No, I'm not going to remove it, but I should add some others so it's not just my strange face posted all the time. So the equivalence principle you can take in a different way and say that if you're freely falling, you feel no effect of gravity. And if you feel no effect of gravity, that really means you're effectively in a flat space-time, okay? Well, actually, I shouldn't say that because this is already preempting the fact that being flat is corresponding to no gravity, implying curvature is giving some gravity, which actually we've not really justified. But I suppose the way I'm going to justify it is by saying that gravity is related to your path through space-time, in that if you're in a freely falling reference frame, if there's nothing supporting you falling in a gravitational field, if there's no floor of the Earth or anything, then you don't feel anything, okay? So there is a relation between gravity and your freely falling path through space-time, okay? So your path through space-time that you follow... Oh, hello, Doe is here. That's okay. Feel free to interrupt. So your path through space-time is related to the gravity that you feel in the space-time, okay? So, now if you kind of think geometrically, well, what should affect your path in space-time? Well, if you think in a total analogy, if you're going for a walk on the Sussex Downs, which is my nearest, the campus where I am is in the middle of the Sussex Downs, so that's my reference point. You're going for a walk in the Sussex Downs, which are very hilly. So your path through 3D space, confined to the surface of... Thank you, Sly. Your path through 3D space, confined to the ground, the 2D hills in the ground, is governed by how bumpy the hills are. Okay, you go up a hill, you go down a hill. And, how bumpy these hills are, you can kind of think of as the curvature of the Earth's surface. The curvature of the literal field. I don't mean field as in a physics field, I mean field as in where cows graze, because there are also a lot of cows around here. The curvature of the meadow, the field, is related to your path through it, okay? So gravity is related to paths through space-time by the equivalence principle, and we can think of paths through space-time as being related to how curved the space-time is. The curvature of the space-time determines which paths you take through it. If there's a big hill, you got to go up, you got to go over the hill, thinking about ordinary meadows with cows and whatnot, in that way. So that gives us a very schematic equation. So far we have gravity is related to paths through space-time. More technically, I should call these geodesics. And what I've just also said is that paths through space-time, I'm just going to copy that, is related to curvature. Curvature of the space-time will affect how you move through a path through the space-time, okay? So, by the kind of transitive property of these equalities I've written, is it transitive? What's the word? I think it's transitive. So, if gravity is related to paths through space-time, paths through space-time is related to curvature, then we can say something quite important, which is that gravity is related to curvature, particularly, I mean curvature of space-time. Well, space or space-time? Okay, this is the interesting thing. Because actually, long before Einstein, I think maybe it was Riemann, had the idea that you could start thinking about gravity, trying to explain gravity as being the curvature of space. Okay, but this is not quite right. Okay, if you just think about curvature of 3D space, that doesn't actually give you gravity. It's interestingly actually the most important part that really gives you, when you take go to the Newtonian approximation, take the Newtonian limit of your general relativistic equations. The most important part is actually the timey component, not the spacey component. So this is not quite right. Riemann, I think it was Riemann, was not quite right in thinking about gravity as curvature of space. I think it was Riemann. I'm going to have to check that because it'll annoy me if not, but I think it is. So it took Einstein to come along and think about, instead of curvature of space, but curvature of space-time, this 4D construction that I think people like Minkowski had pushed this idea about thinking about special relativity in terms of 4 dimensions, 1 of time, 3 of space. Because initially, Einstein didn't think about special relativity in a 4-dimensional way, in a geometric way. I think actually he wasn't very keen on the idea initially of it being thought of like that. But I think it was Minkowski mostly and others that really pushed the idea, realizing that you could talk about special relativity in this way in terms of a 4D geometry, a 4D non-Euclidean geometry, that I don't think Einstein was immediately partial to, as far as I'm aware. But with that interpretation of special relativity as being, a 4D geometry, I think then it almost became quite natural to move on from that to start thinking about gravity as being related to this 4D geometry. So now, instead of space, as I think it was Riemann initially thought, Einstein started to think about curvature of space-time. But, this is all very well and good, very schematic, saying gravity, gravity tittle curvature of space-time, but what does it mean? You're a physicist, you have to write things in equations. So, from what exactly are geodesics? Well, a geodesic is the shortest path through some curved space. So in general relativity, it corresponds to a path that extremizes the proper time of the observer that is moving along that path, but you can think about them in different ways as well. You can think about, if you just think of, say, an ordinary sphere, if you want to get from one part of a sphere to the other, I mean, this is pretty difficult to draw like this, but maybe the path you take, for an observer that is not living on the sphere to look, it looks like you're taking a curved path. But from the perspective of people that are living on the 3D sphere, on this curved space, this sort of equatorial path is the quickest path, okay? So it's what appears to be a straight line to someone living on the sphere, but to someone not living on the sphere, it looks curved. But that's what the geodesic is on this. Exactly, shortest is in the definition of the metric. Yeah, you need a metric to have this idea of the shortest geodesic path. Yep, so it depends on how you measure distances. So in this case of the geometry on a sphere, if you measure distances in a way that is confined to the surface of a sphere, then your geodesics will all be these equatorial curves. They won't just be direct straight lines, because you're not allowed to go directly on a straight line, because it would mean you're cutting through the sphere. Okay, but yeah, exactly. So you have to find a way of formulating these equations, formulating this statement in terms of equations. It does look kind of like the Joker. Yeah, those are the eyes, there's the mouth. I see what you mean. So there's the wisdom that comes from special relativity, like Minkowski had, thinking about this 4D theory, and how they were constructing things using tensors, things that transformed under Lorentz transformations in a way that preserved the form of the equations. So they were again thinking along this same line with general relativity, that they should try and construct equations that are tensorial in nature, in that they transform in a way such that your coordinate system should not affect the form of the equations. Okay? Any observer, any coordinate system, should have the same set of equations, just transformed in an appropriate way, but so that they are form invariant, they look the same. So again, as wisdom from special relativity, the way that you represent matter and energy distributions in special relativity, in this Lorentz covariant way, this way that doesn't change the form, is to have a stress energy tensor. Okay, so your matter part of your equations, however you describe matter in general relativity, should be in this way, with a stress tensor that is in this way, with these tensor indices under what transformations? Well, so under special relativity, it will be under Lorentz transformations, but in general relativity, it's any sort of general coordinate transformation, like a diffeomorphism invariant thing. Okay, your thing should be... what exactly is a tensor? Well, there are a lot of ways to answer that question. In fact, the question is a bit of a meme, I think, because people often say a tensor is something that transforms as a tensor, which is a definition people laugh at, but it's not a bad definition. But there are more slightly sophisticated ways of defining them in terms of vector spaces and dual vector spaces. But for our purposes and for your purpose, a tensor is something that when you transform it, so in our case, when you go to another observer's reference frame, the form of the equation doesn't change. It may be, if you go to another person's reference frame, it's just replaced by t mu nu, but with a tilde on top to show it's from a different person's frame. Okay. I'm sorry, it's not a very good definition. I like to pair that definition with a vector is an element of a vector space. Yeah, exactly. A vector is an element of a vector space. A tensor is an element of, you know, some product of vector and dual vector spaces. But anyway, you can get too formal with these things. The components will be different. Yeah, well, the components will have transformed, but they should have, like, the same form. So say your tensor... yeah, so say, like, your tensor is some isotropic stress energy tensor like this, where rho is pressure, rho is density, p is pressure, like this. This is kind of the standard choice for an isotropic stress energy tensor. It means when you transform this, it should still have u's here, but the u's should have tiddles. In a different metric, if you're going to a coordinate system with a different metric, it should just be the metric with a tiddle, and then you should have the same constants, well, no, different constants, but appearing in the same way that they did in the untiddled version. So you should have the same p here as you do here, but now it'll just be a p tiddle. Okay, so that's what I kind of mean by form invariant, when these things change in this way. But certainly the components of g mu nu may be different. But that's roughly what I mean by that. Okay. Anyway, we don't want to go into too much detail, because you can talk about these things all day. I want to just kind of justify where the equations come from. So we should have justified, are any equations tensorial? No, not all equations are tensorial. Oh well, if they're constructed, so yeah, if you take, you know, combinations of a tensor under a certain transformation, then that thing is also a tensor. You know, like if you contract tensor indices, you can get a scalar or a lower rank tensor or something. Then those things will still be tensors, but you know, it carries quite a heavy meaning, I think, for something to be tensorial in how it transforms. If you multiply a tensor by another random tensor, yeah, like if you had something like a mu nu times b alpha beta, this thing would still transform as a tensor. Yeah, but proving those things are tensors is different. Chris and his toffles would like to have a word. Okay, yeah, that's true. So this thing here, although it looks like a tensor, is not a tensor. The Christoffel symbols. But anyway, we definitely don't want to get into those right now. Okay, so we should have justified that if you're trying to construct your theory in a way that doesn't depend on coordinate system, doesn't depend on observer, you should have this kind of covariant definition of matter distributions, or way of describing matter distributions, like you have in special relativity. Okay. What else do we have? Well, so there's another quite important thing I didn't write here, which is that we sort of expect from Newtonian physics, from Newtonian gravity, that also gravity should depend on your matter distribution. So where you have matter, you should have gravity. Where you have gravity, well, your matter will move in that gravity. But where you have matter, you have gravity is the important part. Okay, so this allows us to now equate these two parts here to get an even more important schematic equation. That matter should roughly be related to curvature of space-time. Okay, that was an important thing I should have mentioned earlier, this second part here. So matter should be related to curvature of space-time in what we've argued. And what I've just said is that, sort of as some wisdom from special relativity, we like to describe matter in this way, as a stress-energy tensor. Again, not going into too much detail. So this tensor here is rank 2. Meaning it's got two of these indices on the bottom, mu and nu. And just like when you're setting, if you've got matrix equations, you can't set a 2x2 matrix equal to a 3x3 matrix. Similarly, you can't set a rank 2 tensor equal to a rank 4 tensor or a rank 3 tensor, whatever. So if I'm going to set matter equivalent to curvature of space-time, oh, no problem. See you later, non-dairy neutrino. Thanks for popping in. So if we're setting matter is equal to curvature in some way, curvature of space-time, that means we need a rank 2 tensor describing curvature. Okay. And there are a few options for how you can do these. The most obvious choice you can make is to have R mu nu, where this is this so-called Ricci tensor. And this is in fact what Einstein first tried after he, went through some similar or different, whatever, logic, I think quite similar logic. But actually this runs into problems. This doesn't give you what you would like to get. It doesn't give you what you'd expect. So what you can do is, that from special relativity, you have a condition on your stress tensor, on your matter distributions, which is that the derivative of your tensor should be 0. And this roughly corresponds to energy conservation and momentum conservation. Okay, it gives you like Euler's equation, for fluids when you put it in, which is a momentum conservation equation. Now in general relativity, this expression is for flat space-time with no curvature. Wait, what happened to what indices? Sorry. Oh, I see. I can put them both downstairs. Then I just have to put this upstairs. Yeah, it's fine either way. Yeah, the upstairs and downstairs, you swap these using a metric tensor. But again, we don't want to go into too much detail. This is all very sketchy. Well, as in I'm just sketching it out. So this is, assuming you can take a derivative in flat space, but taking a derivative in curved space is a little harder. You have to introduce this notion of what is called a covariant derivative, which kind of includes the fact that your space-time is curved. So if you want to take derivatives of vectors, in order to compare them, you have to move them towards each other through this curved space. But again, I'm really being very hand-wavy here. So what you would now expect is, for your GR equation, you expect it to hold when space is flat. You expect it to just give you back special relativity. So you sort of expect that this curved space-time derivative of the stress energy tensor should be 0 in general relativity, because then in flat space-time, this thing called the covariant derivative, which is like your curved space-time derivative, will just turn into your flat space-time derivative, which must be 0. So you expect this thing is also 0. Okay, but because, remember what we're doing is we're setting matter equal to curvature. Here was our matter tensor, and the first try Einstein had was r mu nu, the Ricci tensor. So his first try was to set r mu nu is approximately equal to t mu nu. That was his first go. But of course you expect now, if the curved spacetime derivative, the covariant derivative of t mu nu is 0, if that is sort of equal to r mu nu, that must mean that r mu nu, the derivative of r mu nu, should also be 0. But it turns out it's not in general. There are some spacetimes you can quite easily make that don't have this property, that this derivative is 0. So we've now sort of restricted the case of requirements we want for our rank 2 curvature tensor. We know it should be rank 2, but we also know that whatever it is, the curved space derivative of it should be 0 from this fact here. This kind of GR version of conservation of energy, conservation of momentum. Okay, so you need a rank 2 tensor that... Oh, thank you for the follow, Professor Peter. So you need a rank 2 tensor that has a covariant derivative. When you take the covariant derivative of it, it's 0. Okay, and there's a really powerful identity in differential geometry that was known long before Einstein came along, long before general relativity, but Einstein didn't know it. I think Einstein did not know a lot of differential geometry, actually. Like I was saying earlier, he had to kind of be convinced by, I think, Minkowski, that thinking about special relativity in this geometric way was a powerful and important thing to do. So I think it wasn't in his field, at least initially. Certainly it was, by the end of, towards the later part of his career. But initially I don't think it was. So this identity is really powerful. And this identity is always true. Was it Eddington? No, I don't think it was Eddington. I'm pretty sure it was Minkowski that convinced Einstein of this geometric way of thinking about special relativity, which then was pretty crucial in thinking about general relativity. You can't think about general relativity in a non-geometric way. I'm fairly sure it was Minkowski. So this identity... that is sometimes called the differential Bianchi identity, or possibly sometimes the second Bianchi identity, I can't remember, is always true. It's an identity. So here R is the Ricci tensor from before. G is the metric tensor, which tells you how to calculate things like angles and lengths in your curved space-time. And then this is the Ricci scalar, which you just get from taking the Ricci tensor and multiplying it by the metric tensor, or to think of it differently, by contracting the indices of the Ricci tensor. Okay, now I'm really just sketching out the tensor stuff here. Okay, we're really not going into much detail about this. It's just the motivation of where Einstein's equations come from, what the logical chain is roughly. Okay, so this is rank 2. That's good. There's only 2 free indices here. This combination within the bracket, and it is always 0 when you take the covariant derivative of it, as it should be from saying that this curvature tensor, whatever it is, should roughly be the same as t mu nu, and knowing that t mu nu always has this derivative of 0. When we say scalars don't transform, does that mean its value stays the same in all frames? Yeah, that's correct. If something is a scalar, now, so there are things that So say, for example, you're thinking about special relativity. So you might say, well, density is a scalar. It's just a number. It must just be a scalar when you transform in special relativity. But actually, it's not. It's not a Lorentz scalar. Okay, when you do Lorentz transforms, density actually changes, and you can think about this in terms of length contraction. Exactly. Yeah. If you think about a box, when you're running towards the box, the length shrinks in it, so it gets more dense. So density is not a Lorentz scalar. Okay. So there are lots of these things here I'm stating are tensors and scalars, but really you have to be very careful about what you call a tensor, what you call a scalar. There are certain things are tensorial, like the metric, like the stress tensor here as it's constructed. Actually the stress energy tensor, you have to be very careful in constructing it in a covariant way. But all the things I've used here are real, tensors. Okay. So this now leads us to take this rank 2 curvature tensor, which has this nice property that its derivative vanishes, the covariant derivative. So we now make our second guess for equations describing gravity, or Einstein's field equations. Is there any other tensor whose covariant derivative is 0? Identically 0, not that I know of off the top of my head. It's quite possible there is some, more exotic tensor in differential geometry that is identically 0. But as far as I know, there isn't one. I mean, other than, a lot of the time you can say that the covariant derivative of the metric is 0. That's a choice most of the time you're free to make. But in terms of like a curvature tensor, not that I know of. I don't know. Not as far as I know, though. Okay, so this is our second guess, sorry, for Einstein's field equations. So, we say this thing is tilde, it's approximately equal. Well, now let's say it's equal to a constant times it. Okay. And often I should say, actually, this combination here is often given its own name, g mu nu, called the Einstein tensor for obvious reasons. So more compactly, the way you would often write Einstein's field equations is like this. Okay. Now the issue is just what is this numerical constant here? Well, the way you could go about finding this numerical constant is to say that in the regime where you move away from this general relativity theory and you move back towards Newtonian approximations, where Newtonian gravity is accurate, or sort of small values of your metric around flat space-time for weak gravity. So for weak gravity, you expect your space to be more or less flat, your space-time. So if you do something like you take your metric and say it is the flat space-time metric plus some small contribution, h mu nu, which corresponds to a curved part. And, then what you can do is you can work out g mu nu, which, involves the Ricci tensor, the Ricci scalar, the Ricci tensor is written in terms of the derivatives of the Christoffel symbols. I can never actually remember which way round they go. It's something like this, maybe. And, then there is some products of tensors and a product of different ones with different indices. It looks like this with these Christoffel symbols, which are in themselves actually not tensors, but this combination of them is a tensor. Okay. And then these Christoffel symbols, they themselves are the metric times derivatives of the metric like this. I may well have made some mistakes in writing these out because I always forget what these things actually are exactly. So you can see you've got things that are products of the metric times derivatives of the metric, and then up here that's what each one of these gammas are. Then up here you've got derivatives of these gammas and products of these gammas. You know, so what you would have to do is you would have to find r mu nu to first order in H, plugging in g mu nu into here, 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 and here. Do it all to first order, and then what eventually happens is you end up with something that looks a lot like Poisson's equation, which is a way of writing Newtonian gravity, you know, in terms of vector fields. It's like the sort of the gravity version, the Newtonian gravity version of like Laplace's equation. Okay, so it's the derivatives that make the Christoffel symbol, not tensors. Yeah, exactly, because these are ordinary flat space-time derivatives. So these things here will not transform tensorially under, you know, a general coordinate transformation. They will transform, you know, in a flat space-time coordinate transformation, but actually in flat space-time you can always arrange that these things here are 0. So because your metric will not depend on position in flat space-time. So yeah, that's why these things are not tensors, because these things here are not tensorial. But interestingly, this combination of them, you know, that appears in derivatives of them, a difference in 2 derivatives, and then a difference in 2 different kinds of products with indices in different places, will be a tensor. So r mu nu is most definitely a tensor. So it's not always obvious whether something is a tensor or not. You need to be very careful about it. But for these cases, you know, we know that the Christoffel symbols are not tensors. R mu nu is a tensor, g mu nu is a tensor, and so on. Okay. But anyway, if you do this, you do all this linearization, this weak field gravity, you end up with something that looks like Poisson's equation for gravity. And you can then compare this with what you know Poisson's equation for gravity is, and you can find that this constant here, so you will find that this constant k is 8 pi g over c to the 4th. So in a very hand-wavy way, that is how you would get Einstein's equations. Like that, okay? And there's another way you can get them, involving an action principle. So the, you know, action principles are very powerful in physics. They're a way, you know, like we did when we looked at that mechanics problem earlier, we used an action principle then. We wrote down a Lagrangian, and we said that, or rather, well, we implicitly did. We didn't actually show this, but the Euler-Lagrange equations you get are a result of extremizing a certain action. Okay, and in the case of classical mechanics, this action is the integral over time of the Lagrangian that we wrote down, which is this difference in kinetic and potential energy. Now you can write down similar action principles for a multitude of other physics problems. So you can write down an action principle for general relativity, and you're restricted by the symmetries you expect your equations to have, as for what you can write down as an action. Okay, so you know your action should be some scalar. First of all, it should be a scalar, and it has to be like an integral over space-time, so an integral over your 4 dimensions of space-time, and it must involve scalars, things that transform as scalars in general relativity in this form invariant way. So first of all, what you have to do in order to have a volume integral, you have to choose a volume element which is invariant under these coordinate changes, and it turns out the way to do that is to have the determinant of the metric here. This is just like a Jacobian factor. If you've ever changed integration variables in multiple integration, you know you pick up a Jacobian factor, a Jacobian determinant. This is exactly the same thing. And then you have to think, well, what scalars can I put in here? Some tensors that are related to curvature, important in general relativity, that are that will transform as a scalar under a coordinate, under a coordinate transformation, will not change their form. So there are a few obvious scalar choices. You can have the Ricci scalar. That is certainly the most important one. Actually, this is for vacuum solutions of Einstein's equations. This is all you need. If you now do a variational procedure where you vary your action, so you vary S, the action, with respect to your metric. Now, again, this is I'm not going into much detail here, but then you will arrive at Einstein's equations. I think possibly there's a factor of a half here and some other constants out the front. I can't remember what they are. But if you do this variation, say this variation is 0, that the action is stationary under kind of, changes and variations to the metric, then you get the Einstein equations. But actually there are other possibilities you can have, which are, outside of general relativity. These are what you could call like higher loop corrections for gravity. So you could have an r squared that is still a scalar. It's a scalar in gr times another scalar. You could have something like r mu nu times r mu nu. Contracting these two indices will still give you a scalar. And you can get all these higher order terms in loop corrections, to gr. But the one that gives you the Einstein field equations is just this r. These terms here are higher order corrections, or you can arrange them. You can find the prefactors and the constants that give you kind of higher order correction terms to general relativity. And when people are interested in thinking about low energy effective field theories of quantum gravity. These loop corrections are often what they consider here. How these change, the dynamics of gravity at a sort of quantum level. But that's not my area. But it's interesting anyway. Well, so I think those were all. I think I only had 2 questions. Those 2, they were very good questions though, very interesting to talk about. For me anyway, interesting to talk about. So I'm quite keen to look at a couple of memes now, I think. So please do, if there are any other questions, do feed them through. But I'm quite keen to look at a couple of memes, because if not, this is no longer office hour / physics meme review. It just becomes office hour. So, and also I submitted a few memes this week to the physics memes Reddit page. So I want to show off my own memes, very unashamedly. Next time, could we look at how tensors and matrices relate? Yeah, we can talk more about tensors next time. Yeah, we'll have to how to calculate stuff by changing into matrix forms, like some computational stuff. Possibly, yeah. It depends, because tensors and general relativity, they are heavy topics. I think I don't know. It's almost difficult to. It's intimidating, I think, to get right into them, because it depends what people have seen before. But if you've not seen some of it before, it's quite heavy to get right back into it, to talk about it. So I'd just be a little worried it might be slightly too technical, maybe not too enjoyable. Well, I mean, to be fair, this was pretty technical, actually, what we were just talking about. Maybe I'll have a think. I quite like the idea you gave earlier, actually, of talking about some more like just Lagrangian mechanics problems. I'm quite keen to think about this double pendulum one I mentioned. But certainly in the future, we could do something about tensors, and maybe more broadly something about general relativity. But perhaps not next week. I'll see, maybe. But yeah, it's a good suggestion. But yeah, let's look at some physics memes. Okay. Can you see that okay? Oh good, my audio didn't die. Nice. Okay, what is this then? Washington State University physicists have created a fluid with negative mass, which is exactly what it sounds like. Push it, And unlike every physical object in the world we know, it doesn't accelerate in the direction it was pushed, it accelerates backwards. Mass will accelerate in the direction of the force. Why do I not believe that? But okay. That's a very confused looking Newton. Fair enough. You were listening to a wonderful podcast on physics beyond the standard model. Really interesting explanation about neutrino mass and how decay products possibly lead to the matter-antimatter imbalance. Okay, interesting. Yeah, there's a lot of, this problem of matter-antimatter asymmetry is a big problem in physics beyond the standard model. And in fact, the problem of neutrino masses is also a big problem in physics beyond the standard model. People don't really understand, how you generate neutrino masses, what kind of particle a neutrino even is, whether it's a Majorana particle or a Dirac particle in some way. It's all very interesting. I don't know a lot about neutrinos, I'll be honest, but I do find it interesting. Measuring the current while slowly increasing the voltage was so confusing right after the first peak and before the second peak. After seeing the results from the Frank Hertz experiment for the first time. I don't know that experiment. Yeah, don't know. No idea about that experiment. Could we also talk about how the relativistic tunneling flight time, according to some experiments, may be superluminal? I haven't heard about that. Relativistic tunneling flight time. Oh, as in just normal like quantum tunneling through a potential. I don't know the Frank Hertz experiment. No, I don't think I do. Is it a common experiment? What is it? What have you got? You've got neon gas. You've got an ammeter. Voltage sources. Oh, well, okay. Does it make sense? I'm assuming like when you have a high voltage, it can ionize further. The spark can jump further. So then you've got like a higher. There are more batteries involved in the cell. So like when you've got a lower voltage here, it's not as ionized, so it can only jump this far. So you get the first bump. Then when you go further, it can jump further, and you've got two cells, so now you get a higher max current, and yeah, I don't really know. No, not sure. You learn that for your arbiter, so your secondary education finals. Oh, I see. No, I've never studied that experiment, to my knowledge. But you said if they have mass, is it correct that there must be right-handed and left-handed neutrinos? So I think it's if you try to introduce neutrino masses, I think it breaks this. It means that you have to have neutrinos of different handedness, left and right. Whereas if neutrinos are massless, then the left and the right-handed components sort of decouple. So you only really have left-handed neutrinos that are involved in interactions in the standard model. So if you have masses, then you would also have right-handed components. I think these right-handed neutrinos are sometimes called sterile neutrinos because they don't interact with the rest of the standard model very much. So there are some ideas that dark matter could be these sterile, not standardly interacting neutrinos, as I think. I don't know a lot about it. One of my friends is actually doing his PhD looking at sterile neutrinos. So I could ask them about it, but I don't know a lot about it myself. We left England because we learned I had been lied to my whole life. My family told me air resistance and friction were negligible, but they're not. Nice, very topical. I quite like this meme format. This is where I would put my magnetic monopoles, if I had any. Cool. Yeah, magnetic monopoles are predicted from a lot of certainly from string theory and a lot of other kind of grand unified theories. These things that could have formed very early on as topological defects in the early universe. But I think if they did form, you would expect to see a lot of them, which is, I think, is one of the reasons that inflation in cosmology is useful. That inflation would have sort of diluted all of these monopoles, if indeed they were there. Oh, Professor Peter is raiding with a party of 8. Thank you very much, Professor Peter. Beard gang. Oh, nice. Yeah, very much. I take it from Professor Peter's emote that he is a fellow bearded scientist, I expect. Interesting. Yeah, we've just finished office hour. So we were talking about general relativity and doing quite a cool sort of classical mechanics problem. But now we're just doing meme review. Now we're just looking at some physicsy memes. So we were just talking about monopoles and how I think inflation solves this problem in cosmology called the monopole problem. That you expect that there should be lots of monopoles formed in the early universe by this, like gut phase transition or something, but inflation kind of dilutes them. We're all bearded scientists at heart. I totally agree. Nice. When I try to compute probabilities in quantum mechanics, wave function, normalization constant. That is very important. You've got to normalize your wave function, or else your probabilities might be greater than 1, which is not good. Laughs in general relativity. I didn't follow that meme. Is it Alan Guth? Yeah, Alan. I think Alan Guth is one of these early people that put was one of these fathers of cosmic inflation. 4 phases of matter. Nice. Plasma cat. In this case, we will list the metric convention. Oh, I totally agree. Plus minus minus is it's not a good metric convention. You got to go minus plus 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 for me anyway. Me after conducting the double slit experiment with a torch and a piece of paper with holes. Wave behavior. Kepler's first law of motion, elliptical orbits. She looked very disappointed that our planets aren't very eccentric. Lol, interesting stuff. That's a weird meme. But what is engineering if not physics persevering? Nice. I want to get to the meme that I submitted because I thought it was quite funny. Oh, I like this one actually. This one was good. YouTube physicist, scientist, can't prove the existence of dark matter because you can't see it. Me, Eureka. Socratica is a good channel. What, as in like oh yeah, as in where this one came from. Yeah, no, they did some nice ones on like group theory or something I quite liked. I watched some of those. Water, the coolest water. Okay. Oh, there we go. This is the one I submitted. About neglecting higher order terms. I realized though afterwards, I should have called it, I should have like captioned it, "Don't talk to me or my sum ever again," would have been better. Exactly, terms in the Taylor series. I mean, you never go more than first order. Who needs second order terms? Name a more iconic duo. I'll wait. Ah, Bessel functions of the first and second kind. Very iconic. Very iconic. Classical physics after the ultraviolet catastrophe. Yeah, don't talk to me or my high order terms ever again. Exactly. Pretty accurate, to be fair. Pi equals 3. How dare they? Unstable girlfriend. Fair enough. You just got vectored. Bessel functions are pretty... They can be pretty nasty, I agree. Oh, I like this one. Sad physicist. Now kiss. General relativity, quantum mechanics. That's the idea. Learns Lenz's law. Unlimited power. Good old Palpy. Schrödinger, will you please listen? I'm not the Messiah. Physicists. He is the Messiah. Did Nobel get a Nobel? Erwin Schrödinger won the Erwin Schrödinger Prize. I'm assuming it must have been the first Erwin Schrödinger Prize, or if not, that would have been a bit weird. Like the inaugural one or something. Schrodinger's plates. They're both broken and not broken until you open the door. Fair enough. True. Waves or particles. By this point, it's not unusual for a student to be... let's open it. A little confused. Oh, right. Just out of context. If you get that far in physics, you should be a little confused. When you make a slight error in your explanation of a highly complex and nuanced topic in r/physics. Downvote. Yeah, people are very downvote happy in r/physics. And Reddit in general, I guess. The unspoken agreement between STEM majors that the business degree ain't shit. For those of you taking phys blah blah blah. Is that B stands for business. Because it does no work. Nice. I'd love to go back in time to blow people's minds with my incredible knowledge. But how do you make this electricity? I don't know. Yeah, I think definitely in the last, 100 years, the gap between the technology people use and the level to which they understand the technology they use has got pretty enormously bigger. I think probably, maybe 100 years ago, people would sort of roughly know, or maybe hobbyists anyway, would roughly know how to fix a radio and stuff like that. But getting someone to fix a mobile phone, I think, is a bit of a step up. Non-conservative system would go brr. Yeah, so this is involving a constraint force in your Lagrangian equations. Electromagnetism notes be like, oh, that's a good figure. I would have enjoyed that if someone had put that in electromagnetism notes for a course I took. Oh, this is another one I put. Apple, apple, pair, disappear. Get it? Because it's it's the boundary term you get when you vary the action for a scalar field. And you always assume it disappears somewhere at spatial infinity, that you can set this thing to 0. Also, the question would be, if you understood how to produce electricity in principle, would you know how to make it with the available tools at the time in a useful way? Definitely not. I think, you'd need copper, first of all. The only way I could think to get copper that you could possibly apply to, very ancient times is this technique of phytomining, where they grow plants in copper-rich earth, and somehow the copper is taken up by the roots into the plants, and then if you burn the plants, you can get some of the copper back from the plants in some way. But actually doing it, I think, would be enormously difficult. Getting enough copper to make enough conductive material, and I mean, then you've got to, if you want to do anything computational, you need semiconductors, or you need vacuum tubes and stuff, and those are enormously difficult things to make. Even making a light bulb. Making a filament light bulb, is very difficult. You need some relatively difficult metals for it. You need tungsten for a filament. You need some inert gas for the interior atmosphere, like helium. Helium was only I think typically they use argon, actually, but you say you wanted to use helium. Helium was only really discovered on Earth in the last 100 years or so, 120 years maybe. It's amazing how little we knew even that time ago. That's also how you can mine Bitcoin, grow some Bitcoin plants and burn them. What about the Baghdad battery? What is the Baghdad battery? You'd probably get killed or die of hunger before making electricity. Very true. Very true. And then even if you did make electricity, you could get burnt for being a witch or something, or something like that. Yeah. Exactly. String theorist in space. Wait, it's all strings. Always has been. I wish. One day, 1040 minutes. Oh, that is quite a nice way to remember it. 1040 minutes. I am best at short wavelengths. Vine's law. I am best at long wavelengths. Rayleigh-Jean's law. Bagové. I don't know what that means. Planck's law. So better keep a Latin or ancient Greek dictionary with you if you get teleported. Better keep a... Yeah. You you could convince some people you were the devil or something. Start chanting Latin and then use your electricity. From Wikipedia, the Baghdad battery or Parthian battery is a set of 3 artifacts which are found together: a ceramic pot, a tube of copper, a rod of iron. It was discovered in modern Kujat Rabu, Iraq, close to the metropolis of blah blah blah, the capital of the Parthian. Huh, interesting. I didn't know about that. So people thought they were making like a battery, or you know, people had made a battery in like the Parthian Empire. That's interesting. Vine's law. Is it Vines? I say vines. Or sometimes wine, but I say Vines. That the object functioned as a galvanic cell. Oh, I see. Interesting. Huh. Yeah, no, I hadn't heard of that. That does sound interesting, though. Vine's law always works, though. What Vine's law is this? What, like T lambda max times T is equal to this constant that's what, like 2.898 times 10 to the minus 3 or something. As far as I know, it always works. I guess you would just... Maybe it doesn't always work. I suppose the way you would find it is you would take the Planck's law, the Planck distribution, which tells you, you know, the frequency of this black body radiation law, and then you just find the maximum of it. You know, you find the wavelength that corresponds to the maximum value of the number density of particles that have a certain frequency at that given temperature T. So as far as I know, it would always work. I suppose it maybe is not so good in that when you have... well, yeah, no, I don't know, actually. I mean, at high temperatures, the Planck distribution, it sort of shifts to the right and becomes a lot flatter. So I guess, you know, using it when you've got a long wavelength at oh wait, no. Yeah, no, I don't know. I don't totally get that meme. I don't want to fixate on it though. Aim for the moon. If you miss, you may hit a star. Entirety of astronomy and astrophysics. I might joke to you. Yeah, stars are pretty sparsely distributed. You'd be quite unlikely to hit a star if you went out in any one direction. This isn't mine, but I found it on Google and thought it was funny. I thought it would fit in well here. And God said, and there was light. Wow, that got 2.4 thousand likes? Interesting. This is like an old thing. You know, you can buy this on t-shirts and stuff. It's barely even a meme. It's like just or, you know, it's a very 2000s meme. He's not wrong. You may hit a star. That is true. Very, very vanishing probability, though. Other people, Netflix and chill, me. What is that? Plus. I can't even tell what they're doing there. Plus V equals D. Plus V equals... I don't know what they're writing there, to be honest. T dot V equals... Yeah, like... TV equals D? I'm not sure. Oh, I see. Oh, TV equals R. Oh, thank you. I'm far too innocent to notice these things in these memes, but thank you. Magnets be like plus plus minus. Oh, I don't like that. That's kind of implying monopoles. Well, I mean, hopefully there are monopoles, but I probably don't think. Still very uncertain. But yeah, they've drawn this like these are magnetic monopoles. I wonder if anyone has commented on that. I don't want to downvote it because that'd be quite rude. Yeah, exactly. There we go. Magnetic poles, positive, negative. Yeah. He knows that Newton's gravitational law comes from Kepler's law. Oh, came from Kepler's law. Yeah, that's true. Newton figured it out kind of in reverse from the fact that he realized that in order to have orbits that were elliptical, you had to have an inverse square potential. And it was known from Kepler that planets moved in ellipses. So Newton, you know, I mean, he had to invent calculus to show it, but he could show that if you have elliptical orbits, you have to have exactly a 1 over r squared potential. Classical mechanics be like F equals ma. Sum of force minus change of momentum times di is 0. Euler-Lagrange equations. Variation in action is 0. I mean, this one exactly implies... Well, actually, to be fair, if there are no... This only exactly implies this one if there are no boundary terms, which there may well be. Inverse square force or potential. Oh, sorry, inverse square force, yeah. If I said inverse square potential, of course, that's definitely a verbal typo. How Zoom affected physics education. According to the video clip you watched on What is Physics, air is a 1 form of energy. Take your breakout group partners. No, air is not a form of energy. Okay. Oh, right. But apparently air is a form of energy. Huh. Something about that seems a little bit dodgy. I came across this pre-lecture slide and I didn't quite understand why there is a picture of Drake. Drizzy got mass. I don't know enough about Drake to understand that reference, sadly. Sheldon and Leonard conversation anime version. Theoretical physicist. Gravitons must exist because the quantum theory has successfully explained every other force of nature. How can we verify it? We need about a galaxy-sized particle accelerator for it. Experimental physicists. Give up on your dream and die. Yeah, we are probably never gonna get a particle accelerator that big. Because he started from the bottom. Where was it? Oh, there it is. Oh, possibly. Yeah. Did he do that song about started from the bottom, now we're here? I really don't know. But if he did, then that makes sense. Oh, this was the other meme I submitted. Maldacena go brr. D plus one-dimensional gravity theory and anti-de Sitter space. D-dimensional boundary conformal field theory. This is a beam about the ADS-CFT duality. Exactly, yeah. I thought it was pretty funny. It didn't get as many upvotes as I thought it would, but I guess maybe ADS-CFT is a little niche. I don't know. Well, anyway, I think it's probably about time for me to head off. I still have an enormous amount of marking to do this evening and this week, sadly. But thank you very much for coming. The questions today were really good. If you fancy it, you can, if anyone hasn't already, you can join my Discord, and we occasionally share memes and talk about other questions for next time to do on there. And what I'll do is I'll update the Google form for next week's questions if anybody wants to submit them. But yeah, then I guess we'll leave it here. You just give them all zeros, call it a life lesson. I wish I could do that. Oh, who are we raiding? Ah, yeah, I haven't thought about who to raid. I see the only person really online I can see that I follow is Astro Canuck is live, so we could raid them. That would be good. But before I do that, I guess I'll just say next time, well, so Thursday, you can come back and do some Mario Kart. We'll do some Mario Kart. Boring math professor just went live. Yeah, sure, okay. Let's do it. I do just do exclamation mark raid, then boring math professor, don't I? Or is it slash? Oh, I can't actually remember. God, I'm an idiot. How do I do it again? That shows how long it's been since I actually did a raid. I really should get into the habit of doing it more because it's a slash. I'm an idiot. Yeah, thank you. Okay, yeah, let's do that. Let's raid them. But yeah, then we'll call it a day. And yeah, I'll see some of you on Thursday. And yeah, thanks all for coming again. Join the Discord if you fancy it. And I'll see some of you next time. Okay, all right. Bye. Well, let's do the raid as well, actually. But yeah, see you guys later. Bye. Oh, thank you for the follow. The Hangs May None. Okay, see you in a bit.